Hello, friends. Welcome back to my YouTube channel. This is the third part of my discussion on mass transfer coefficients. And today I will be talking about K-type mass transfer coefficients. So in part number 1, I had introduced turbulent diffusion to you. In part number 2, I discussed F-type mass transfer coefficients. And now in part number 3, I will be talking about K-type mass transfer coefficients. So at the end of this discussion, you will be able to define K-type mass transfer coefficient. So let us move on. So in order to understand the concept, we are going to consider a case of turbulent diffusion. In this case, the scenario is like this. Air is flowing under turbulent conditions past a pool of water. Water in the pool is almost stagnant, and during the contact between water and air, some water evaporates into the air, and then the resulting water vapor diffuses through air, which is under turbulent conditions. So this is a case of turbulent diffusion. So this is the pool of water, in which water is almost stagnant and air is flowing past the water surface under turbulent conditions. So water, it evaporates into the air, and the resulting water vapor diffuses through this turbulent air. So this is a case of turbulent diffusion. So you have a pool of water in contact with the air that is flowing under turbulent conditions. So this is water. I'm going to denote water by E. So when it evaporates into air, the resulting water vapor will be A, which will be diffusing through air, and air we are going to denote by capital P. For our discussion, we are going to consider, or let me first tell you, when the air is flowing past water surface under turbulent conditions, then close to the water surface there is a thin film of air. What is the significance of this thin film? Within this film, the conditions are laminar. So you can say that this is a stagnant film of air which is close to the water surface. So for our discussion, we are going to consider this direction as X direction. So air is flowing in X direction under turbulent conditions, and this is Z direction. So water vapor is diffusing through air in the Z direction. So as you move away from the surface, when you start your journey at this point and you move away from the surface, you are passing through the stagnant film. That is, you are initially in laminar conditions, and then you move on into turbulent air, and as you move away from the surface, the conditions become increasingly turbulent. Then for our discussion, we are going to consider one point, that is on the surface of water. Let the concentration at this point be Ca1. Concentration of water vapor at this point in the gas phase. So this point is in the gas phase, but it is at the boundary between air and water. And then we will consider another point away from the surface of water, where concentration is Ca2 in gas. So there is a concentration gradient, and due to this concentration gradient, water vapor is diffusing through turbulent air. That is the case. So let us move ahead. Okay, so let me take this diagram in our discussion. So as we move away from the water surface, conditions become increasingly turbulent. I have talked about it. So at the surface, when you are at the surface, there is a thin film of air where the conditions remain laminar. And in the laminar layer, molecular diffusion is predominant. So when you are in the thin film close to the water surface, molecular diffusion is predominant. And as you move away from the surface in the turbulent zone, turbulent diffusion is predominant. So as you move from the surface into the turbulent zone, you are moving from a place where molecular diffusion is predominant to a place where turbulent diffusion is predominant. So I hope you have understood the scenario. If you have any doubts, you please mention them in the comment section. Let us move ahead. So now our objective is to describe rate of mass transfer from the surface to the turbulent zone. That is, the objective is to describe mass transfer by turbulent diffusion. We need to describe it. That is the objective. And for that, we are going to use the concept of K-type mass transfer coefficient to get the rate of mass transfer under turbulent conditions. The mass transfer involved as water evaporates into the air, the diffusion of water vapor, which we are denoting by E, through air, which we are denoting by B. Then molecular diffusion is predominant in the laminar layer. We have understood it because in the layer close to the water surface, conditions are laminar. And when you move away from the surface, turbulent diffusion is predominant. Turbulent diffusion is predominant in the turbulent zone. So our objective is to describe rate of mass transfer for the case where molecular diffusion is predominant in the laminar layer and turbulent diffusion is predominant in the turbulent zone. Let us move ahead. So since both molecular diffusion and turbulent diffusion, they are involved, we need to consider both of them. So considering molecular and turbulent diffusion, we can write, or you can modify the mathematical expression for Fick's first law. So now the law will be written like this. JA is equal to minus DAB plus ED into DCA by DZ. And I'm going to call this as equation number 1. So in this case, JA is molar flux of E relative to the molar velocity of B. DAB is the diffusion coefficient or diffusivity of E in B. And ED is the mass ED diffusivity. So the mass ED diffusivity describes mass transfer by turbulent diffusion, and DAB, it describes mass transfer by molecular diffusion. DCA by DZ is the concentration gradient in the Z direction, and the negative sign in equation 1 indicates that diffusion is taking place in a direction of decreasing concentration, or mass transfer is taking place in a direction of decreasing concentration. Let us move ahead. Now for given A and B, that is, this is a case where water vapor is diffusing through air. So if A and B are fixed, then DAB will be constant. DAB is going to remain constant at constant temperature and pressure. But ED, the mass ED diffusivity, depends on local turbulence conditions. So it is almost zero at the surface. So when you are at the surface, DAB is predominant. ED is almost zero at the surface because here conditions are stagnant. So ED, it depends on local turbulence intensity. How? It is almost zero near the surface, but as you move away from the surface, it increases with an increase in the distance from the surface. So as you move away from the surface, ED will come into picture, whereas when you are at the surface, ED is zero. As you move away from the surface, ED will increase. DAB, it predominates in the laminar region. So why in the laminar region? Because molecular diffusion is predominant in that region, and ED will be predominant in the turbulent zone. You need to understand this. So as you move away from the surface of water, this equation will get modified. Initially, DAB will be predominant. On the surface, ED will be 0. Then as you move away from the surface, ED will start becoming predominant. So I hope you have understood the use of this equation, how you are or how you can use the equation to give mass transfer rate under turbulent conditions. Let us move ahead. So we have the equation JA is equal to minus DAB plus ED into DCA by DZ. That was equation number 1. So if I rearrange it, it will be JA into DZ, that is equal to minus DAB plus ED into DCA. So this is a differential equation, and then you can integrate it. So at Z is equal to 0, that is when you are at the surface, CA is CA1, and at some distance from the surface, at Z is equal to any Z, let us say that CA is CA2. So if you integrate this equation, it will be integration from 0 to Z, JA into DZ, that is equal to integration from CA1 to CA2 minus DAB plus ED into DCA. Now, what are the constants that are present in the equation? JA is constant under steady state conditions, so that can come out of the integral. DAB is constant for given A and B, and under constant temperature and pressure, DAB is constant. But ED, it varies, and this variation is not known. As you move away from the surface, ED will change. But how it changes, it is not known. So what is done? An average value of ED is considered to be constant. We take average value of ED bar in this equation, and it is considered to be constant. So in that case, DAB plus ED bar, this group will be constant, and that can come out of the integral. Let us move ahead. So we have this equation, integration from 0 to Z, JA into DZ is equal to integration from CA1 to CA2 minus DAB plus ED into DCA. So J is constant, it will come out of the integral. So JA into integration from 0 to Z dz, that is equal to DAB plus ED bar, and this negative sign I will make it positive by interchanging the limits. So it is DAB plus ED bar. Now this is average value, which is constant, so that's why it has come out of the integral. So DAB plus ED bar into integration from CA2 to CA1 DCA. So now limits are from CA2 to CA1. So now let us integrate. So JA integration of DZ is Z, limits are 0 to Z, that is equal to DAB plus ED bar, and integration of DCA is CA, limits are CA2 to CA1. So when you apply the limits, it will be JA into Z minus 0, that is equal to DAB plus ED bar into CA1 minus CA2, that is JA into Z is equal to DAB plus ED bar into CA1 minus CA2, that is JA is equal to DAB plus ED bar divided by Z into CA1 minus CA2. A simple integration. So you get this equation for J. Now in this equation, this group DAB plus ED bar by Z, this is a parameter, and that is nothing but K-type mass transfer coefficient. So I am denoting it as Kc. So this is K-type mass transfer coefficient, and the subscript C indicates that the concentration difference, in this case it is expressed in terms of molar concentration difference. So with this, Kc is the convective mass transfer coefficient, and it is similar to convective heat transfer coefficient. So it is the K-type mass transfer coefficient which we had planned to understand. So K-type mass transfer coefficient is given by this equation, and Ja in this case is molar flux from the surface relative to from the bulk phase. So in this case, when you write this equation, when you have the equation after integrating the modified Fick's law, in that equation Ja would be molar flux from the surface area relative to from the bulk phase. So the molar flux from the surface area relative to molar flux in the bulk phase. So that is Je. So therefore you have Ja is equal to Kc into Ca1 minus Ca2. So this is the defining equation for K-type mass transfer coefficient. Ja is equal to Kc into Ca1 minus Ca2. So this is how K-type mass transfer coefficient is defined. Let us move ahead. So let us write proper definition for K-type mass transfer coefficient. The defining equation is Ja is equal to Kc into Ca1 minus Ca2. So that is of this form: molar flux is equal to mass transfer coefficient into concentration gradient. So therefore mass transfer coefficient is equal to molar flux divided by concentration gradient. So with this equation, you can define a K-type mass transfer coefficient in the following way: the molar flux per unit concentration gradient. The molar flux per unit concentration gradient is nothing but the K-type mass transfer coefficient. And in this equation, we have concentration gradient expressed in terms of molar concentrations. There are different ways of expressing concentration gradient. So for gases, it could be partial pressure difference. The concentration gradient could be in terms of partial pressure difference. It could be in terms of mole fraction difference. It could be in terms of molar concentration difference, as is the case in this equation. Then for liquids, the concentration gradient could be in terms of mole fraction difference, and it could be in terms of molar concentration difference. So in this way, there are a number of ways. So for each of the concentration gradient, you have different type of K-type mass transfer coefficient. So depending on the concentration gradient, you have the K-type mass transfer coefficient. So simple way of defining K-type mass transfer coefficient is the molar flux per unit concentration gradient. So let us move ahead. Our concentration gradient is nothing but the driving force for mass transfer. So you can also define K-type mass transfer coefficient as the molar flux per unit driving force. So let us move ahead. Now, before I end my discussion for this video lecture, let me introduce some special K-type mass transfer coefficients. These I will be discussing in detail in part number 4 in my next video lecture. Here I am just introducing them to you. Special K-type mass transfer coefficient. So special K-type mass transfer coefficients, they are defined for two most frequently occurring situations in mass transfer operations. So for two most frequently occurring situations in mass transfer, we have special K-type mass transfer coefficients. Which are the two most frequently occurring situations? One is A diffusing in non-diffusing B, you know that, and the other case is equimolar counter diffusion of A and B. So for these two situations, special K-type mass transfer coefficients are defined. But while defining this this special K-type mass transfer coefficients, we will be using N type of molar flux rather than J type of molar flux, because that would be better. So we will know about how different mass transfer coefficients come into picture. I will be discussing them in my next video lecture, as I said. Here I am just introducing them to you. So it would be molar flux, the defining equation. Molar flux is equal to mass transfer coefficient into concentration gradient or the driving force. So in terms of N, that would be Na is equal to mass transfer coefficient into concentration gradient. So there are, as we understood just now, there are different ways of expressing concentration gradient, and therefore for each case there are different types of different K-type mass transfer coefficients. So for each type of concentration gradient, you have one mass transfer coefficient. So I will be discussing in detail about this special K-type mass transfer coefficients in my next video lecture. For now, for this video lecture, I will end my discussion. So at the end of this discussion, you must have understood how K-type mass transfer coefficient is defined and how it is different from F-type mass transfer coefficient. So you should be able to tell what is the difference between F-type mass transfer coefficient and K-type mass transfer coefficient. So if you have any doubts, you please mention them in the comment section. For now, I will end the discussion. In my next video lecture, I will be discussing special K-type mass transfer coefficients. We will be getting the defining equations for different K-type mass transfer coefficients. So thanks for watching this video lecture. Do subscribe to my channel. Tell your friends to subscribe to it. Hit the bell icon so that you will be notified as soon as I upload any new video on my YouTube channel. In my next video lecture, I will be discussing different types of special K-type mass transfer coefficients. For now, have a nice day. Bye-bye.